Thanks for joining us. We'll discuss how to do an aerodynamic study of a wing that was designed for 3D printing and was assembled using 3D printed parts. We will cover a real-time CFD simulation run from Ansys Discovery using the screaming fast video card GPUs. We'll also calculate drag force and drag coefficient, and lift force and lift coefficient. Before we start on that, we need to review how drag and lift forces are calculated. One type of drag force is pressure drag. This represents pressure on the wing, which is normal or perpendicular to the surface. It varies in magnitude across the wing. Pressure and stress are used interchangeably where they both are force per unit area. Viscous forces are referred to as shear stress or skin friction. They represent the forces tangential to the cell surface, acting across the first cell thickness. The drag force is then the summation of these forces in the x direction. The lift force is the summation of these forces in the y direction. These are stored as stresses in what math heads call a stress tensor. They use this term to scare engineers and technicians even though it's just storing stresses in the x, y, and z directions. One great feature of Ansys Discovery is you can parameterize dimensions and create multiple variations that can all be analyzed in real time. The history tracking feature allows for the simplest way of creating the wing angle parameter. Once the parameter is created, multiple variations can be set for CFD analysis. In our case, we chose 0 to minus 20 degrees in increments of 2 degrees. So, as Ansys Discovery steps through the simulation, starting from 0 degrees, angle of attack, it solves very quickly using the video card GPUs. The RTX 5000 has 100 cores. If we look at task performance, we can see the CPU activity is low. But the GPU is near 100%. This is what allows the fast, real-time simulation. So, the big question is, how accurate are the results? The color contour plots look great, but how accurate? One method is to compare the results to some known quantity. There is a website called airfoiltools.com, which has a variety of airplane airfoil shapes which have been analyzed in great detail. If we look at the NACA 4412, it has a similar shape to our wing, but inverted to cause lift of the airplane. So, if we analyze the aircraft airfoil and compare it to the data on airtools.com, we should conclude that analyzing the 3D printed wing should have the same level of accuracy. We will consider 1 position, 0 degrees, angle of attack. The NACA 4412 airfoil data ranges from 0.0075 to 0.0175 at 0 degrees, angle of attack. In Ansys Discovery, we analyzed the wing at 3 levels of fidelity: low, medium, and high. These all run from 0 degrees to minus 20 in increments of 2 degrees. Solving utilizes the screaming fast GPU cores, which solves in minutes, not hours. We then analyzed the wing in Ansys Fluent using a k-omega turbulence model with y plus equals 1. This required a very fine mesh and took 4 hours to solve. So, if we compare the results, we start with the low and high range of the NACA data at 0 degrees angle of attack. This is shown by the orange box. All 3 Discovery results and the Fluent data are inside this box, indicating agreement with airfoiltools.com and assumed high degree of accuracy. Therefore, we can assume our 3D printed wing analysis using Ansys Discovery Explore feature will provide a fast and accurate drag force analysis. This provides a means to quickly solve multiple position CFD analysis, taking advantage of your graphics card GPUs. So this is the final design. 3D printed sections that are dowel pin connected to produce a rigid wing design, providing significant downforce and minimal drag. Thanks for watching this video, and leave any comments below.